So, flat earthers claim that there's no real gravity, that what is really happening is that we have density and we have buoyancy. And they say that those terms alone can define what we experience as the gravitational pull from the Earth. Let's put that claim to the test. Hi, I'm Michael Hansen. I'm a physicist from the University of Copenhagen. I have a master's degree, Master in Science of Physics, and I have recently for some time now, spent some time arguing with flat earthers about various topics about physics. One of the things that I think is brought up again and again is the idea that we don't have gravity. What we perceive as gravity, the gravitational pull from the Earth, the reason that I can stand here and not float away, the reason why my phone, which is now recording, can actually measure the pull or whatever it is from the Earth, is not because of the gravitational pull and the physics that is hereby derived first from Newton and then from Einstein, but rather density and buoyancy. So first we need to have an idea of what we're dealing with. So we're going to make a drawing. Here we have a balloon. Alright, so we have two formulas sort of governing the idea of buoyancy and the idea of gravity. Gravity you all know, I hope. Fg is equal to m times g. I'm going to take another marker here. Green one. And buoyancy is often defined as rho, which is the density, times the volume, times g. Now, you hopefully know that you can actually derive the mass of something by taking the density, and multiplying it with the volume. Then you get the mass of something. Alright, let's keep that in mind up here in the corner. It's equal to rho times volume, or density can be said to be, not density, volume can be said to be, let me see, mass divided by density, I think it is. Let's see, yes, that's true. Alright, so one of the things about buoyancy here is that it was first defined by a Greek man called Archimedes, or as we say here in Denmark, Archimedes. I'm not sure which is correct. What he said is that the buoyancy something experience is equal to the amount of volume of sort of oppressed matter. So if I take sort of a wood stick and put it into water, then because the wood has a lighter density than water, then the buoyancy force from the water will be equal to the volume that the wood stick displaces. I'm going to show you an example here now where we use a balloon instead. As you can see, I've tried to make a drawing here of a balloon, and then I'm going to go further into that. One of the things that you might notice is that both gravity, of course, is dependent on this gravitational acceleration constant here, g, but also buoyancy is defined or dependent on this gravitational constant here. One other thing is, as you can see here, density, it's a property of matter. So if I have this marker here, obviously it's made of plastic, and that plastic has some density, but density does not define any force. And that's a problem, because if you only have buoyancy, which is a force, and let's for the time being sort of exclude this dependency here, but just look at the idea of buoyancy, that something is pushed up because it has a lighter density, then we obviously have a problem, because we need another force. Can you see that? Because, I hope you can see it, because if I erase this force here, or if I put it equal to this force here, then nothing happens. If this force here is gone, then everything would float, because there would be only an upward force. So, and let's just make these, sorry about that, try to make them sort of roughly equal. And we also have this dependency here, right? So we have, if just to look at it as sort of a function of density and buoyancy presents some problems, because if we only have density, then we need some way to define what does that density do? Because density is not a force. And if we only have this, density is applied here. That is correct. But if we only apply this force here, or this formula here, then we have sort of a problem, right? All right. So I'm going to present to you now, hopefully, I guess, a way to calculate whether our balloon here will float or not. So it's a balloon filled with helium. All right, so the first thing we need to do is we need to define, we need to look at the ideal, the equation for the ideal gas. So let's take a look at that. I have now put the ideal gas not the ideal gas constant, the formula for the ideal gas up here. So we have pressure, the volume. So pressure times volume is equal to the molar number, the number of moles, times this gas constant here, which I have defined over here. It's 8.3144 cubic meters, that should be a meter, times the pressure in Pascal, divided by the temperature in Kelvin, and the the number of moles, particle number in moles, if you will. The gas constant here times the temperature in Kelvin. So we can use this formula here to get an idea of, if we say we have some gas of helium, and we want to figure out how much density does that gas have, because obviously that depends on a lot of parameters, the temperature, the volume, and so on and so on. Some of them we can say we fix, but we need to calculate it nonetheless. So the first thing we can do is that you can see we have the volume here. But also before we define that the volume could be said to be equal to, let's see, yes, mass divided by the density. Let's put that in here. So we have pressure times the mass divided by density is equal to nRT. All right. So now we can move things around a little. So the first thing I would like to do is divide by pressure. So we get mass over density is equal to nRT over the pressure. Because we're interested in getting the density, we can now divide by the mass. So that would get us 1 over density is equal to nRT over nP. but we're not interested in the inverse, the inverse of the density. We're interested in the density. So we get density is equal to mp over nRT. There's one more thing we can do, because we have m here and we have n here. Now there is another definition in gas physics, or chemistry for that matter, that the molar mass, big M, is equal to the mass over the number of particles in moles. That means we can redefine our equation to be density is equal to mp over RT. This is the formula that we're going to use in order to figure out the amount of density, the density of the helium we have in our balloon. So let's just put sort of in short notation what the idea is. So the buoyancy here is defined by the amount of displaced air by this balloon. So the buoyancy is defined by the density of air, not the density of helium. But obviously, because we have helium inside this balloon here, it has a certain weight, it has mass. So obviously the gravitational pull also works on the balloon and also on the helium. I think that's obvious for hopefully everyone. So that's how we're going to calculate it. So the buoyancy we calculate by looking at the volume displaced by the balloon. Gravitational pull is basically everything else, the mass of the balloon and the mass of the helium. So let's continue. Alright, so now we are ready to calculate the density of this balloon of helium. So as you can see, I've put in the constants we're going to use here. The molar mass of helium you can find, it is 4 times 10 to the minus third kilograms per mole. Not a mole like the animal, but yeah. Again, the gas constant 8.3144 cubic meters times the pressure divided by Kelvin times mole. We have the pressure because we obviously going to calculate this for the balloon being at surface level roughly. So we have that the pressure at surface level here on Earth is 1 atmosphere, which is also 101,325 Pascal. And finally, I have said that the temperature of the air is roughly something like 20 degrees Celsius, so that is roughly 293 Kelvin. Remember that also if you want to make a physicist or a chemist happy, say Kelvin, not degree Kelvin. There's no such things as degree Kelvin. There's degree Celsius and then there's Kelvin. Just a little by note. Alright, so from here on now, it is just to plug in the numbers. Let's do that. So we have the density of helium is equal to 4 times 10 to the minus third kilograms per mole times 101,325 Pascal divided by 8.3144 cubic meters. Sorry, it should be Pascal here, not just pressure. Pascal, Kelvin mole times 293 Kelvin. That gives us 0.1644 kilograms per cubic meter. So this is the number that we're going to use in our future calculations. So let's calculate what we actually want. We want the mass because obviously we're going to calculate the gravitational pull on this balloon here, the helium. So we're also going to need the mass. So let's find the mass. First we need to figure out, we have a 5, I haven't said that yet, but the volume of the balloon is 5 liters, which is also equal to 0.005 cubic meters. Perfect. Now I'm going to have to shuffle around behind the computer in order to find that. Alright. So the mass of our helium balloon is, well, volume 0.005 cubic meters, because we have the density in kilograms per cubic meters, times 0.1644 kilograms per cubic meters, which gives us roughly 8.32 times 10 to the minus 4th kilogram. Obviously I'm going to erase this board, but you can, if you want to follow these equations, then write these numbers here down. I'm going sort of to try to give you an idea where the important numbers are. Alright, let's continue with the calculations. So now I've put in some more important numbers here. These important numbers here we have already used and are no longer really needed, but I have kept them there. We also need the volume of the balloon, we have it here in cubic meters. Now we have the mass of the helium in kilograms, which we have here. And also I have said that the mass of the balloon itself, that is the plastic, and this is probably set way high, but it's roughly 5 grams. So that is 0.005 kilograms. So the combined mass here is 8.32 times 10 to the minus 4 kilogram plus 0.005 kilograms, and that is, let's figure it out, 8.32 and minus 4th plus 0.005 0.00582 kilograms. I hope you can read that. 58832 kilograms. So now we can calculate, that is m times g. So we have 0.00582 kilograms times 9.82 meter per second squared, and that is equal to, if my calculations on this paper is correct, 0.057 Newton. So this is the gravitational pull on the balloon and the gas itself, but now we want to figure out how much does this displaced volume of air push on our balloon. And for that we need the density of air itself. And of course the atmospheric air is made of all sorts of things and is dependent on the temperature and so on and so on. In fact, if we wanted to do it the really correct way, we also needed to calculate the density of air by looking again at the ideal gas formula as we did before, and then take the molar mass of all the constituents of air itself. We're not going to do that because of time constraints, so we're just going to use a rough estimate of the density of air at sea level. So we have now the density of air. It's roughly 1.225 kilograms per cubic meters. So let's go on and calculate the buoyancy. The buoyancy force was defined by the density, in this case of air, times the volume of our balloon, times G. So let's put in the numbers. So we have, and sorry, not G, but B, buoyancy. Continue this line down here. So, what do we have? We have 1.225 kilograms per cubic meter times volume. Well, that was 0.005 cubic meters times 9.82 meter per second squared. And that gives, if my calculations are correct, 0.060 Newton. These are rough estimates. So we have, let's recap on the numbers that we had. So we had the gravitational force on the gas, and the balloon was 0.057 newtons. The buoyancy given by the displaced air, atmospheric air, was 0.06 newtons. So as you can see here, if I should define this, redefine it, I would write it like this. So we have the balloon here. As you can see, the force of the buoyancy is just a tad higher than the force from gravity. But nevertheless, that means that the balloon will rise. This is how we can calculate and figure out these things. Now you can also see, I could replace this buoyancy calculation here. I could calculate the buoyancy for both the helium and the air. But that wouldn't make sense because buoyancy is an upward force, not a downward force. Even flat earthers agree on that. But if there's only an upward force, because again, density is not a force. It's a property of matter. There's no force vector, there's no force calculations defined in density. So that doesn't work. So as you can see again, if I remove this, if I say, okay, there's no gravity, then I hope you can hopefully see the obvious problem here. Because no matter what I put in here, no matter what material, I could put lead inside that balloon. And because there's no downward force, there's only an upward force, it should rise. So we need that downward force here, which is defined as the gravitational force. And I can keep saying the same thing, and we will probably never agree, but I need to see some hard math, some calculations where flat earthers show exactly how they see density as the bringer of some force. Now, there is a thing here, because density and volume, if you put them together, you can get the mass. If you take the mass and the gravitational acceleration, you get a downward force that is a weight. That is exactly what happens when you stand up on your bathroom scale and look down and get horrified. It's because there is a pull, you have mass, and that mass is the same everywhere. If you go to Pluto, if you go to Jupiter, well, Jupiter is probably not a good example because it's mostly gas, but if you go to Mercury, if you go to Venus, if you go to Mars, if you go here on Earth, you go to the Moon, your mass is the same. Your mass is the same everywhere in the universe as long as you don't do anything to change it. And obviously because the body is an ever-changing environment, Your mass is not exactly the same at all times, but you could say that you have a rough estimate. So basically said, your mass is the same. Your weight, on the other hand, is defined on how much any kind of object is pulling on you. And obviously, even as I'm standing here, there is a buoyancy force. The air is pushing on me. But because my density is so high, and that means that my mass is relatively high, the Earth is pulling on me on roughly 1,000 newtons, something like that. I have a mass of roughly 100 kilograms. Then I needed to have a really light density and also a really big volume in order for the air to push enough on me to go upwards. That is why I don't float around. But if there were no downward force on me, and that's the thing that I really can't understand why flat earthers can't understand. What we are talking about here is a downward force. Hopefully, every flat earthers can agree that we have mass. Hopefully also every flat earther can agree that we have, that there's something pulling things down, whatever we want to call it. We call it gravity in physics, but we could call it bananas or Rupert or anything like that. But there is something pulling us down, and those combined give us a force. We can measure this force many different ways. In the physics lab, in high schools, we use these little Newton meters. It's basically a spring which is calibrated to different newtons, and we can measure how much force the Earth is pulling on anything actually. So the real basic outline of this argument here is, in order to have buoyancy, in order to use buoyancy for anything in a world where not everything floats around. My book doesn't, I doesn't, our couch doesn't, my monitor, my screen here doesn't, this glass of wine doesn't. We need some downward force. That downward force cannot be density. Think about it. Then it would mean that we would have Fg. Yeah, sorry, not the wrong Greek letter. Rho times G. But that doesn't define that's not in that wouldn't be consistent with what we can measure. It doesn't work. We could redefine it to say, well, it's also density times volume times G. But here we need to be very clear on what it is that we are calculating, because this would be the density of the helium and the density of the balloon, and the volume of the helium. The volume of the balloon would be very hard to figure out, because the volume is a very slight little slice, right? That wouldn't be 5 liters. So using G like this would be redundant and silly, but it could be done. But it would still give us that the gravitational force is equal to the mass of something times the gravitational acceleration. And then, as I have said many times, actually comes from the very simple formula that the force is equal to the mass times the acceleration. Alright, so I hope that I have sort of given you an idea how you can calculate these things. I hope also that I have given you an idea here why we need both gravity and buoyancy in order to have something rise up, and more importantly, something that doesn't rise up or float up. If we didn't have gravity, that would essentially mean that if you throw a stone out into water, the stone could be lying on top of the water. Now, I'm going to make another video. This sort of be one video out of 2. I'm going to make another video where I calculate these 2 things here, just for the sake of argument, using the buoyancy formula in both ways. But my argument is that we're going to end up either with something that is rubbish, doesn't make sense, or the exact same thing, just a very, very, very much harder way to calculate it. So, see you around.